So in this presentation, we'll look at exploring MTU with Suzieq. We'll start with a quick definition of an MTU and then explore what your network has with respect to MTU, the idealized view that you think it should be there, what is really present, and how do you go about understanding that in your network. From the perspective of definition, when people say MTU, they typically mean the IP MTU, and the default value of that is 1500 bytes. And the IP MTU, as shown in this figure, consists of the IP header, the TCP header, or essentially the protocol header. It could be UDP2, of course, and the payload. But in addition to the IP MTU, there is also something called an Ethernet MTU, which is essentially the size of the payload, the IP MTU, that is we just talked about, plus the L2 header. And that's typically 1518 bytes by default. In most networks which are not tunneled, you will tend to see these sizes of 1500 bytes as the default MTU. Inside the data center, many people set the MTU to be a larger one, such as a jumbo size frame. And when you look at a tunnel network, such as with EVPN, the ISL ports are set to jumbo MTU so that they can carry the VXLAN traffic effectively. The server-facing ports and the SVI have a value that is lower than the jumbo MTU in order to enable the addition of the VXLAN header without overflowing the MTU size. And what value this lower number is of the MTU depends. In some networks, people set that MTU to be a little less than the jumbo MTU. Like if it is 9216, they set it to say 9200, and not 9200, less than, I say 9186 or something. And then let the TCP MSS handle the issue, or they keep the server and the SVI to be at the MTU of 1500. And they typically do this because if you're going to an external network, they are worried about fragmentation, and you do not want fragmentation. There are lots of problems that a network can face and an operator can have to troubleshoot with. And if you do a search in Google, you'll see lots of different real world problems that have been reduced or caused because of MTU mismatches. So Suzieq makes MTU a first-class citizen, and we'll look at what is done in the next in this demo. To start with, we'll look at the topology, and this is the topology that we use in most of our demos. It's a classical enterprise data center topology. You've got inter-switch links, which should have an MTU that is a jumbo size. You have a bridge, a server-facing link, which should be essentially the 1500 bytes, the default MTU, and the external MTU, which should also be 1500 bytes. Now let's take a look at, so you expect to see when you look inside your network and you say, I explore my network, I expect to see 3 different MTUs or 2 different MTUs, essentially the inter-switch link MTU of 9216 and the server-facing port and the external-facing port MTU of 1500 bytes. But let's see what it really looks like. So we start from the topology as usual, and we go on from the status page of Suzieq. We go into the Suzieq's Explore page and click on the interfaces, which is where the MTU information is present. When you do that, the summary information that is presented right away tells you that there are 9 different MTU values present here. If you look at the unique MTU count, there are 9 of them. And you say, wow, that's pretty strange. I was expecting 2, and why do I have 9? So in order to know what those 9 different values are, you can drill down by looking at the distribution count here, and you see what those different values are. You see that there are 1500 byte packets. That's the largest number of interfaces. There are 433 of them. And then there are interviews with a size of 0. Then there's a size which is 65536. That seems pretty high. And then there are other different various ranges of MTU sizes that all look strange. Let's start investigating what these different sizes are by drilling down and saying, what is the size 0? Size 0 typically happens to be an MTU, an interface that is down, but let's figure that out. Instead of just assuming that, let's say by adding a filter here, only show me interfaces that have an MTU of 0 is what we are saying. And when we type that, we see that the red link indicates that this is a down interface. Because the NXOS instance comes with all the interfaces as admin state up, but they are not really connected. They are all down. And so these down interfaces have unconfigured interfaces have an MTU of 0. A proper configuration would ensure that all of these are in admin state down, so these errors wouldn't show up at all. But anyway, we clarified that the MTU 0 is admin state down. So let's kind of filter that out in our MTU calculation and say like, okay, what if I just say that I want to only look at up interfaces for all my calculations? And when you do that, you notice right away that the unique MTU count didn't really come down, that there are 9 interfaces. There are still a handful of interfaces, about 6 of them, which have a value of 0. That's a configuration mismatch, and we'll look at them later. But let's investigate the other odd MTU sizes. Let's look at this MTU of 2000. Why is there an interface that has an MTU of 2000? What interface is that? And if you go in here and you say, I want to see all interfaces which are size 2000, you will see right away that the interface is something on a host name called DC Edge 1, which is our internet facing router, which is a Junos box, and the interface name is BME0, which is an internal interface. So it's an internal interface that has an odd MTU size of 2000. This is never seen outside. It's all inside the chassis of the Junos, so to speak. So this is irrelevant to the discussion. Okay, so now let's kind of go on to look at some of the other MTU sizes that we saw. Let's say like, okay, I want to see what else is there. We saw an MTU of 65536. What is that? What are those interfaces? When you type on that, you see that they are essentially server interfaces, which are the loopback addresses. Similarly, there are also information on these. Some of the spine interfaces have a value of 65536. This is an artifact of Suzieq. You can ignore that. But the DC edge ports have also a bunch of internal facing ports, which all have 65536. So we can say like, okay, this again looks like an internal facing interface MTU or a loopback MTU. And so we can ignore those for a second. Let's look at where the BGP peering happens, because when a BGP peering happens, you want to make sure that those interfaces have the same MTU. And interface peering happens between the leaf and the spine switch ports. So let's kind of drill down, and we can type here and type. If you can notice, one of the things we are doing here is we are not leaving the Suzieq screen. We are looking on the same screen. By just changing the filters and querying the data, we are able to understand what is going on in our network without having to log into a single box or go into multiple places. So if you use that and you hit enter, now you'll see all the loopback ports, and you see right away that the loopbacks have essentially 1500. We know the 65536 are server ports, and you can see that they're all server ports. Those are the only ones that are loopback and the firewall. But everybody else on the spine and the leaf all have 1500. This loopback on the spine interface, which is loopback 1, is essentially an interface that is not used. It is a configuration bug that created loopback 1. We need loopback 1 in the other cases because that's the one that's carrying the VTEP IP address. But in the spine case, it's created, but it's not really used. And that's the default one. So we can say like, okay, so 0 is not present. Every peering on loopback 0 is on 1500. If you've done the right configuration, loopback 1 wouldn't show up. But coming back, we know that all the other interfaces which have loopback 0, all of them have interface of 1500 bytes. And so that looks good. To kind of make it more precise, you can kind of drill this down further and say, if name equals loopback 0, because we know loopback 0 is what NXOS devices use. So if you type that, you would see right away that all of the devices that are loopback 0 across all of the different switches have 1500 bytes. We see that the device count is 8, and we see that there is only one device, which is this particular information. So all the spines and the leaves, if you click on this, it'll sort on that. And you can see that you've got all the exit leaves, leaf 1, 2, 3, 4, spines, all of them are 1500. So this looks good. What about the ISL interfaces? So we can kind of clear this filter. Just add back state equals up and continue our interface MTU analysis. So we saw that everything looks good. what is this 9000? So we can say like, okay, I want to see what is the interface which is 9000. And you'll see that those are all the SVI interfaces. The SVI interfaces should be, this is not correctly configured, the SVI interfaces should be the same size as the server facing ports. So if this is 9000, the server facing ports which should have been present here as well with 9000. So this is a configuration error that you need to fix. So let's take a look at what about the, what is the word for it, server facing ports. We know that they are all dual attached, so they are bond interfaces. So we can say like, I want to see our port channel interfaces, which are called bonds in Linux. So you can say I want to see all interfaces that are of type bond. And what you get right away is you see that all of these are 1500 bytes except port channel 1. And port channel 1 is really the VPC. And that is the reason, and NXOS doesn't allow you to configure them, and the VPC interfaces are the 9216s. But all the other interfaces are 1500, but we notice that the SVI has a different interface value, MTU value of 9216 or 9000 actually, and that needs to be fixed. So you can troubleshoot all of this by just using the Suzieq GUI screen. You can look at just MTU and channel down, drill down, not channel down, drill down specific information, filter out different fields, different ports based on various criteria, and understand what your network needs to do. Now, one of the important things with respect to MTU is that you want to make sure that the two ends of the interface have the same MTU. And you can validate that by running an interface assert with respect to Suzieq. When you run interface assert in Suzieq, it runs the checks to make sure that the two ends of the interface are configured correctly. And one of the things it checks is the MTU. And so asserts have passed, and you say like, okay, perfect. So all the interfaces are configured correctly with respect to there being no mismatch between the two ends of the interface. But that's not the only problem that can happen. You can also have two endpoints which have been configured with different MTUs, but now are trying to communicate with each other. All the MTUs are properly matched with respect to peer interfaces, but when you're going from a source to a destination that's multiple hops away, maybe there is a problem. In order to troubleshoot path problems, you would go MTU problems, you would go into the path page and you would type in, and here let's type in between two servers what the path is and hit trace. And let's take a look if there is a problem here. And what you get is this topology, which immediately indicates that there is no problem, because all the links are either black, which means they are routed interfaces, or they are purple, which means they are a tunneled hop, meaning that their packets are VXLAN encapsulated on these. So there are no interface mismatches in between server 101 and server 301. And if you look at the path MTU is 1500. It says that you cannot send a packet greater than 1500 bytes and expect it to get from server 101 to server 301. If you look in between on any one of these links, it'll tell you that the MTU is actually 9216. As we said, ISL links are configured with jumbo values, and therefore they have an increased value, but the path MTU is just 1500 bytes. That concludes this presentation. If you are interested in exploring Suzieq more, please go to the Stardust Systems page on Suzieq, and we point to this because it's a single landing page which gives you details about Suzieq, as well as links to the documentation, the GitHub repo, the how to download and start playing with it, because this is an open source multi-vendor tool, and also how to engage with the community by joining the Slack channel. With that, we come to the end of this presentation. Thank you so much.